Ok, primeramente agradeciendo su presencia aquí en el SMTA aquí en Chihuahua. Entonces también agradeciendo su presencia aquí en la primera conferencia. Entonces aquí vamos a presentar el PCB Fabrication y nos va a ayudar aquí a dar esa conferencia Jerome Larez. Él tiene 30 años de experiencia ya trabajando con la fabricación de tablillas tanto rígidas como flexibles. Entonces esperemos primeramente que explique todo su material y si tenemos preguntas al final de la conferencia se las podemos hacer saber, ¿no? Entonces él viene de la compañía Next Gen PCBs y pues aquí se los dejo para que les muestre todo su material. Adelante.
Muchas gracias. Bienvenidos a todos. Oh, sorry. Me llamo Jerome Larez, like he said, and perdóname porque no puedo hablar español muy bien, so voy a decir esta presentation en inglés. ¿Está bien? Okay, so we're going to talk about the PCB fabrication process from start to finish. We'll talk about different finishes for the PCBs and then some common defect modes that we see during manufacturing and that may result on your end where you guys are assembling the PCBs. I know he said that we can wait till the end for questions, but if you have questions, we're a small crowd. If you have questions during the presentation, please feel free to ask. Sometimes it's good. People are thinking the same thing. And if we want to talk about something, I'm more than willing to talk about it. So let's see. Let me start this. I'll go here. Let's see if we can get this to work. Give me a second here. I guess maybe we'll use the arrows. So I'm going to start very simple just to define what a printed circuit board is. I know we've all seen them, but it's simply a printed wiring, a printed version of a wiring harness. So wiring harnesses with cables and connectors, all the printed circuit board does is just simply organize the wires into an efficient manner. And it also provides a mechanical base for the components. So it's a very simple definition, and you can have several layers. I don't know if you're familiar with that, but you can have several layers of the printed circuit boards. Oh, excuse me. There are different types of printed circuit boards. So there are rigid boards, which are most common in the industry. They're there to electrically connect and mechanically support components. There are also flex circuit boards, thinner by design and enable connections, electrical connections in 3 axes, or where bending is part of the application for any device. And then there is a combination of rigid flex circuit boards that provide the mechanical support for some heavy components, but also provide flexibility. And there are countless applications for circuit boards, so countless designs. Every circuit board is custom. If there are assembly houses in here, assemblers in here, you understand every design has its own unique set of circumstances on how to build it. So similar with the PCBs. For each type of PCB, each type of PCB can have 1 to several conductive layers. The highest layer count I've seen is 40 layers personally, but they have gone higher. And layers refers to the conductive layers, the copper, so the circuitry. There are other layers of substrate, solder max, the green color that we see. So there are several other dielectrics or materials that are involved in circuit board fabrication, but whenever, as a PCB fabricator, whenever we talk about layer count, we're talking about the conductive layers of a circuit board. This view here, the stack-up view, the cross-sectional view of the circuit board is very important in fabrication. So when we see a stack-up, we understand generally about 80% to 90% of what the fabrication process is going to entail. So the first thing I look for in a fabrication drawing is, what does the stack-up tell me? How many layers? And then I understand, okay, what the fabrication process will be. So this is a 4-layer design here as an example, and typically we have core material is what we call it. There's the dielectric, which is FR4 is probably the most common. There are other types of materials. And then there's copper foil on top and copper foil on bottom. So the material comes in this manner. And then we have pre-preg or glue, if you will, and then we use copper foil for layer 1 and layer 4, and we laminate them all together. This particular stack up here is a more complicated stack up. It's a 6-layer design, and it will have through vias, and then a via is just a small hole that's not used for any surface mounts. It's just for electrical connection. It has blind vias, so a blind via is a small hole that you can see from one side, but it's blind from the other side. You won't be able to see it all the way through. You have buried vias, so there's just internal layers where there's vias inside making electrical connections. And then you have staggered vias, stacked vias. These are essentially blind vias, but the conical design you see here, that's laser processing. So lasers are used to drill these small vias and then we plate them, and you get your electrical connection from layer 1 to layer 2, or layer 1 to layer 2, 3, and so on and so forth as you go through the stack up. And please, again, if there's questions, stop me. We can have conversations about it. So again, we're just going to go through the fabrication process in general. And so we'll start with material prep, and this is called out on the fabrication drawings we see. We go through the inner layer processes of imaging and etching the circuits, and then we have an inspection for all internal layers, and then we laminate all the layers together. After that, we begin drilling. So we're drilling the vias, the holes that will create the electrical connections from one layer to another. We then metallize the hole by copper plating the vias and the holes, and then we go through the same process for the outer layers. We outer layer image, we outer layer etch. This is where really the plating, the imaging, and the etching processes are really where the guts of the circuit board are made. After that, we go through an inspection process, and technically by the copper etch and inspection process, you have a functional circuit board. Many times fabricators, if it's a very difficult design, will perform electrical tests after these processes during this inspection step to determine, do we have enough yield? Is there any problems with the process? Do we need to start over, start a remake? But after the etching and inspection processes, we go with the solder mask, which is the coloring of the insulation technically of the circuit board, the silk screen, the metal finish, electrical tests, and then the final routing, and then final inspection. What we have here, just some examples of plating baths. If you've ever been to a circuit board fabrication process, there are a lot of wet processes. So there's a lot of chemistry involved because we're manipulating metals. We're plating and etching gold. We're plating and etching nickel and copper. And so sulfuric acid, nitric acid, cyanide, very nasty chemicals are used for printed circuit board fabrication. And so this is just a plating bath, some conveyorized machineries for developing. These are CNC tools. These are spindle tools used for drilling, and then some inspection tools and inspection tools. So we'll continue on. And again, any questions, please feel free to ask. So I'm going to go back. This is the first part of the process, the material preparation. So engineering will review the stack up provided by the customer, and the customer will call out the materials, the thicknesses, the prepregs, and they give instructions to the fabricator. Many times, these are not, from the PCB fabrication side, these are not set in stone. If the materials are not necessarily available, not every thickness with every core thickness with every copper thickness is available, the fabricators are given leeway to change the stack up before they start building the boards. If it's not allowed to change, typically an engineer will put, hey, no deviations or something of that nature within the stack up. The overall goal is to get the finished thickness within the specification, and then we can manipulate the internal layers as needed. So the material comes in again as these laminations or these bare laminates with copper foil on top and bottom. This is a core material here. In this particular case, we're looking at 4 mils thick, 4/1000 of an inch, or what is that, 0.1 millimeter, and then 1 ounce copper on both sides. And then you can see the prepreg and the glue. There are several different types of prepreg. Each has its own type, its own content of epoxy and resin, and each has its own dielectric properties. So sometimes the stack-ups are very loose, if you will. Sometimes they're very specific, and you have to adhere to them. So it all depends on the PCB application, the PCB engineer, and very early on, the applications engineers, such as myself, we get involved with the designers and the electrical engineers to finalize the stack-up before we begin the fabrication process. So the first stage after material prep and you pull the correct core materials and the coppers is to perform the inner layer imaging process. So it's a PCB, which stands for printed circuit board. It is a printing process just like you take pictures. So you get your material, which is copper clad laminate. This is copper on one side. You have your dielectric or your substrate in the middle, and you have your copper on the bottom. And you literally coat or laminate photosensitive film onto the material. It's just heat and pressure, and it laminates, the materials laminate through, and this film is what gives us our picture. So The designers will give us a particular design. We take their Gerber data, is what it's called, and we load it into a laser direct imager, and the laser will come across and expose the film and harden this film. It's photosensitive, so the light will hit it, it will harden it, and then the film that is not hardened stays soft, if you will. And then we simply develop the unexposed film off. So this is this is the lamination process where we coat it, then we image the film, and then we develop the film. Very similar to any picture. It's just a printing process. In this particular case, we're covering areas that we want to keep with copper, and any exposed copper there will be etched away in the etching process. And that's where we're at now. So it's a conveyorized machine. It is sprays on top and bottom at certain angles and at certain pressures, certain chemistry. There are different types of etching chemistries. And you have, you have your exposed copper. So here's a finished inner layer, if you will, with film covering the film, film covering the copper, and exposed copper other places for the etching process. You just simply run it through the etcher. The film protects the copper we want to keep. Any exposed copper is etched away, and then we simply remove the film. So this is the printing process of a circuit board. Now, it's very simplified. There are numerous rules about how small things can be, how big things can be. There are several different types of film used for different copper weights. If it's very thick copper, you may need thicker film to survive the etching process, because the thicker copper will be exposed to the very harsh chemistry during the etching process. And then this is a cross-sectional view of what it would look like. You have your laminate, you have your full copper foil, everything is shorted there. You have just a pattern of resist. Then you go through the etching process, and it clears out these valleys, creating the traces, and then there's still resist on there that then later gets stripped away in the dry film stripping process. And that's essentially how a PCB is built from a very simplified standpoint. After the inner layers are finished and we have our etching process complete, we then go to an AOI, or automated optical inspection process, which you guys have similar for PCBAs, and it's just comparing the Gerber data from the designer to the actual panel, the production panels, and it's just looking for anomalies. Are there any opens? Are there any shorts? Sometimes lights reflect differently, and we can change the lighting function just to ensure that our traces and our conductors are per the design. So after the AOI process, the inspection process, we then laminate all the inner layers together. So it's basically a cake, if you will, or a sandwich. There are many, as we saw in the first stack up, there could be several cores with multiple layers, or this could be just a simple 4-layer design where you have copper foil, just like aluminum foil. It sounds very similar to aluminum foil like we used to bake, but it's just simply copper foil. We laminate it using prepreg, which is the glue. We have our layer 2 and our layer 3, which is the inner layer core. You have more prepreg, which is the glue, and then the bottom layer, copper foil. We laminate it through heat and pressure. And during the lamination process, there is, similar to PCBAs, there is a rise over run. So you don't want to go too fast in your lamination process. You can create warped boards. It can bow and twist. You want to go at a certain rate of heat and then extend that full baking period, lamination period, and then step down, very similar to PCBAs. After the lamination process, now we go to the drilling process. So drill machines move in X, Y dimensions, and then the spindles typically stay still, and the spindles are running at certain revolutions, and they even have a feed and speed rate that they have to adhere to for the type of metals that we're going through, because that could be very thick copper or thin copper. And a typical CNC drilling machine would have anywhere from 3 to 5 to maybe 6 spindles, and then you can have multiple CNC machines. So you're drilling the circuit boards are stepped and repeated onto a production panel, and you're drilling you can stack the panels up and drill several panels per spindle, and then several panels per machine. So at a large volume fabrication process, you're drilling maybe, I don't know, 20, 30 panels at once, where it is a small prototype shop, you're drilling usually one panel at a time. The next process after drilling is the metallization of the hole. So after drilling, all we have is exposed copper, or you have copper on the surface and the internal layers, and then exposed bare laminate. nothing is making electrical connection from the outer layers to the inner layers. So we start with a seed layer of copper. So the electroless copper is the most common type of metal that is first applied to the whole wall. It is a series of cleaners and conditioners to prepare the panels, and then it's an electroless copper. So it's a chemical reaction that applies copper onto the whole wall, and it's a very thin coat. It's maybe about 5 microns. The second most common is what's called shadow or black hole. It depends which shop you're at. But it adds a very thin conductive carbon to the whole wall, and it is, I think, palladium is what the main conductive material is, but it adds it to the whole wall. But either way, we need to soft metallize the whole wall before we copper plate with electrical copper plating. And that's the first process for getting an electrical connection from one layer to another. At this point, everything is shorted, nothing has been printed. The inner layers are printed and etched, but now we're just starting to make the first initial connections from the outer layers to the inner layers. Then we move on to electrolytic copper plating. Now, electrolytic copper plating, you need electrical connections. You have an anode, you have a cathode. It's similar to a battery. It's in a chemical process, and you can plate full production panels like this, where the whole panel goes in, and it gets plated normally to anywhere between 20 to 25 microns. Some military applications require maybe 30 microns of plating, but that's IPC standards, lies about right there. 20 is the min. Sometimes they allow 18, but that's getting too much into it. But copper panel plating was an older technology. Some of the Chinese shops still use it in mass production. Most fabricators now go to a pattern plating. So both have gone through the electroless copper or the shadow process. Both have conductive colloids on the whole wall, but now we're putting the hard copper on there that's going to be eventually finished with another metal finish. But this is where the first connection from the layers gets finalized, if you will. So copper panel plating is before the imaging process, and pattern plating is after the imaging process, and we'll talk about both here shortly. So the panel plating, as you can see here, this is a plating line. There are multiple panels racked up together. These are the plating solutions in here, and it gets put into the solutions. These are anode bards right here. The cathodes are actually the panels, and there's big solid copper anodes that go the full length of the bath. Actually pretty cool to see. And you plate the entire panel. You're plating the surface, you're plating the whole walls, everything is shorted, everything is connected. And this is a stack-up view. Again, the stack-up is a very important view for all PCB fabricators. You have your dielectrics, you have your base copper, which is the foil, and then you have your plated copper. You're adding more to the surface, you're adding that same amount to the whole wall, and then onto the surface here. So this cross-sectional view is very common in PCB fabrication. So after the copper plating process, we go through outer layer image. So just like inner layer image, it is the same 3-step process. It is a lamination process with photosensitive film. We then expose that film to light, whether it could be a laser, it could be a UV light. It's very sensitive in those rooms, so you use yellow lights, you don't have normal light bulbs. And then we develop the film just like you would a piece of picture. And anything that's exposed to light is hardened. The film stays on there. Anything that's not exposed to light gets developed away in the developer, and you have your panel ready for the etching process. Again, we're covering areas of copper that we want to keep. We're exposing areas of copper that we want to etch away, and then we go to the outer layer etching process. Same thing as the inner layers. The film is covering areas we want to keep. The film is not on areas we want to etch away, and then we strip the film off, and we have our more or less our finished printed circuit board in theory at this time. So again, it's just a printing process, and that's how the circuitry is defined. So this was a very common process in the 90s, but as we came around the turn of the century, more fabricators started the pattern plating process. So in this particular case, after you go through the electroless copper, and it's a very thin seed layer of copper, we then go through the image process first. The difference here is that we're exposing copper we want to keep and covering copper that we eventually want to etch away. So it's the same thing. Here's a whole wall or a via. You have the film that goes onto the panel. You image the film. It's photosensitive light. But in this case, now we're exposing the traces we're exposing the pads and we're exposing the whole walls, and we're just going to plate the circuit pattern. This is a much more efficient way of plating the holes, and it reduces waste, but also because of technology has advanced and all the features has gotten smaller and smaller, this has enabled us to make our traces smaller, our pads smaller, which makes your guys' job harder because you guys are assembling the smaller circuit boards. But and in all reality, what drives technology are the components. So if the components get smaller, then our features, the designers use the components to make features smaller, then we have to evolve how we build the circuit boards, and then you guys have to evolve for how you assemble the circuit boards. And it's a constant flow. And I have some circuit boards here that I'll show you guys, some brand new developed, coming out of product development engineering teams. But overall, it's just an evolution of technology that is constantly going to change. So in this industry, for all of us, we have to love change, because change is constant. And even every design is different. And I tell people who ask me about building circuit boards, and I tell them, I use the Forrest Gump line, it's like a box of chocolates. You never know what you're going to get. Until you get there and until you actually build it, then you start learning where your weak points are at, where your strong